In the last video, we walked through how ERA was using the von Mises equivalent for determining the load limit curves for tension and torque. And it's important now to create a little bit more complicated well and point out what ERA is doing and assuming by default, and how that may or may not create a situation where we've got the incorrect assumptions. So this is a directional well. We've got some dog legs here where we're building angle. It's our original example where we had added some real surveys to create tortuosity in the path. You can see that we've got dog legs on the order of 3 to 3.5 degrees per 100 foot. And I have a tapered drill string here of 5-inch and 5.5 drill pipe, 5.5 S135 on top, 5-inch S135 on bottom. And what we're looking at now are the tripping loads when we're pulling out of the hole, running in the hole. And at the moment, we're not rotating. So this is not a back reaming or down reaming situation. It's just pulling out or running in. Now you'll notice that the limit curve for tension has some irregularity to it. And that can be described in a couple of different ways, as well as the torque limit curve. Remember, this is just for the tube. It's not the connection. And I've intentionally removed the makeup torque curve. It actually, our lowest limit would actually be makeup torque in this case. If I go back to the limit feature and turn on the makeup torque for rotating off bottom, there we go. As you can see, that's actually the lowest value as opposed to the tube. But if for some reason I was using high torque connections or I create a more complicated load case, then the makeup torque might not actually be my limiting factor. But by default, you typically see that makeup torque limit curve. I'm taking it off for the time being just to try to reduce a little bit of confusion. So you'll notice that the maximum achievable torque before we exceed the limitations of the tube changes as we get deeper. Part of that has to do with increasing tension as the string gets deeper, but also due to dog legs that are in the well. And if any of these limit curves ever start not making sense, what I would encourage you to do is switch to snapshot view and then drag the string up and down the well bore to see how the loads change in the string depending on what your bit depth is. And if you noticed when the bit was real shallow in the well, we had a low torsional, lower tensile capacity, a higher tensile capacity than when we got below 1,000 feet. So when we're way up here, real shallow, we flip over to the snapshot view. This is before we got into any kind of dog legs and bending. And you notice as the string gets deeper, due to those dog legs, the tensile capacity goes down. So our limiting factor is governed by this point right here. And then, of course, the string gets deeper and deeper and deeper. We get increasingly more tension, but we also have the introduction of the 5.5 drill pipe, which starts to change the load profile. Okay, so let's see what is actually going on behind the scenes here with our limit curves. You'll notice that when we're in snapshot view, this is not too much of a problem. But when we're in driller's view, this limit curve is based on some background friction factor. And actually, the limit curve could be drawn depending on whether or not you're rotating off bottom, pulling out of the hole, or running in the hole. What ERA assumes by default for any tripping load analysis is that the limit curve is based on the pickup operation. And if you were to click this tab that says limits, you can see that there's a great many different limits that can be displayed on the plot. For example, the helical buckling limit, the rig hoisting limit, the tube tension limit when I'm picking up, the tube tension limit when I'm slacking off, and the tube tension limit when I'm rotating off bottom. And then, of course, we have a whole host of limit curves for the connection itself. Very rarely is the drill pipe connection the limiting factor. That does start to come into play, though, when we're talking about casing or liner. Anyway, back to what we're wanting to focus in on. You'll notice that by default, ERA has assumed the base case or middle friction factor. 0.2 is my average friction factor for the base case, and that is what's being displayed right now. Now, manually, I could go in and choose to display a different friction factor by just clicking on the curve or shutting off this tube tension limit for the 0.2 case. Now you notice it's not labeled as such, it's not labeled a 0.2 friction factor, and we chose to do that just to try to eliminate confusion for customers who are not used to seeing all these different curves in the plot. We could have just had every single limit curve drawn on the plot, but that requires a lot of real estate and explanation. Now, for this particular example, it doesn't make a big difference whether or not I have a 0.3 friction factor or a 0.2 or a 0.1 friction factor. You notice there is a slight difference in the curves, but it's not significant. If I was to set up a different load case, and what I want to do now is backream out of the hole. So I'm going to come on down here to the RPM input and say that I'm backreaming at 120 RPM. And you'll notice that the loads change as well as the limits. Notice that the limit drastically reduces. Now that's due to the introduction of a torsional load in the string. Notice the torque plot over here on the right. We've got torque for reaming down, torque for reaming up, and torque for rotating off bottom. What this limit curve is assuming, of course, is the torque that's in the string when I'm backreaming or picking up. And the friction factor curve is going to be directly linked to not just the pickup friction factor, but the torque friction factor. So if I was to choose 0.3 or 0.1, notice how now these limit curves look much, much different, a much more substantial difference on that limit line. And as it turns out, it's the higher friction factor case that results in a lower limit. That won't always be true, not for all load cases, but for this particular example it is, because it's the higher torque friction factor that results in a higher torsional load in the string, which means I have less tensile capacity to work with. And if I was to pull up the torque plot, I would see something similar. And what I'm going to do here is just remove the slack offs and the rotating off bottom, just show pickup only. We'll pull up the limit curves, and we'll just look at the torsional limit for picking up at low friction, medium friction, and high friction. I'm not sure why we're not seeing all of those displayed. That's interesting. Let's see here. 0.3, there we go. So it would appear that we do have a bug at this stage. It's not displaying the pickup friction factor limit curves. We'll get that corrected, but in the meantime, what you should know is that these limit curves will look differently depending on whether or not we're picking up, slacking off, or rotating off bottom. In this case, the reason why we're not seeing as big of a difference here for torque as we did over here for tension is because there's not that much of a difference in tension. Remember, the torque plot is a direct reflection of how much, the torque limit curve is a direct reflection of how much tension there is in the string, whereas the tension limit curves are a direct reflection of how much torque there is in the string. Likewise, hoop stress, radial stress, and bending stress, but right now what we're manipulating is the tension or torque in the string. If I was to turn on the pumps and start circulating, you would notice the limit curves would change once again because now I've introduced the hoop stress component. And there they change back. All right, so that is a load case where you would want to be extra diligent and careful to make sure that you're displaying the friction factor that you actually intend to use as your most likely case. We've assumed by default it's the base case, but if you're hovering around a higher friction factor, then you would want to make sure and turn on that higher friction factor limit curve. And then go back to the defaults here, reset that, and then turn off my makeup torque and return the scale to where I had it. Okay, that's where we were. Another load case that could get you into trouble is not necessarily backreaming, but just pulling out of the hole. And what we're worried about here now is if I've got a drill string that has much different strength in the two different tapered sections. So I've got 5.5 drill pipe on top with S135 material and the 5-inch drill pipe on bottom. I'm going to change to E grade. And if that's E grade pipe and it's much, much weaker, let's just look at the snapshot right quick. Notice that the snapshot shows me that I am very much closer to the loading in the tube down here in the E pipe than I am in the S135 5.5 pipe. Now, where does that come into play? If we go back to the driller's view plot, notice how we have this kind of stepped curve as the string is moving down in the wellbore. What I'll do is come back to the snapshot, and we'll just we'll watch how the loads change depending on where the 5" is located. Of course, here's the crossover. That's where the 5" is. When the 5" is across the build section and I have all that extra bending stress, I'm very close to the different load curves. And as I get deeper and I get that 5" out of the build section and down into the tangent, and I relieve that bending stress, now all of a sudden I've got a lot more operating margin. So what we'll see is that the operating envelope is going to open up for me once I get that pipe out of the curve. And we'll flip back to driller's view, and you can see that on the driller's view, that's exactly what's reflected in the limit curve. As I get deeper, I get a little bit more margin between my load and my limit. Now, remember that that limit curve is assuming a friction factor. If I scroll down, what's drawn is assuming the 0.2 or the middle line. If I was to show a 0.1 or a 0.3, in this case it turns out that a 0.1 friction factor actually has a lower tensile capacity to work with as a limit than if I had a higher operating friction factor. It all depends on where the load is reaching its limit first. If we flip back to the snapshot, and we just basically manually do what ERA is doing automatically, and that is to say to ourselves, all right, how much overpull would I need to have at the bit before this curve starts to intersect the limit? And we could just, through trial and error, start adding overpull in 10,000 pound increments. Let's just look and see. Okay, 30. Looks like it's going to take a little more than that. 90. Let's see here. Looks like it's going to be about 95. All right. At 98,000 pounds overpull at the bit for a 0.3 friction factor, which is this load curve right here that my cursor's on, you notice that we max out across the dogleg in the build section in the 5.5 pipe. The 5.5 is my limiting factor for high friction factor cases. Now, if I didn't have a high friction factor, if it was a low friction factor like this 0.1, obviously I could apply more overpull, but is it necessarily going to be the 5.5 pipe that reaches its limit first? As it turns out, no, it's the 5" pipe. The 5" drill pipe touches the limit curve first before the 5.5 does, because of the shape and profile and load distribution of the tension in the string. So the key takeaway here, what the message is that you want to be careful when you're looking at a driller's view plot and you're interpreting these limit curves. Is the limit curve that's being drawn representative of the friction that I'm experiencing at this particular point in time? If it's not, then we should go in and manually change what friction factor is being used to display those limits.